Hi folks, welcome to 4.1 Related Rates. So let's talk about some of our learning objectives. By the end of these videos, I hope that you can express changing quantities in terms of derivatives, find relationships among the derivatives in a given problem, and use the chain rule to find the rate of change of one quantity that depends on the rate of change of other quantities. So at the end of these videos, come back, make sure that you've got a hold of all three of these learning objectives. Okay, so let's start with this example. So let's say we have a balloon and we start to fill it with air. I think you would all agree with me that the radius, the surface area, and the volume are all going to increase for this balloon. So another way to say that is that the radius, surface area, and volume all change with respect to time. And so what we mean by that is we could have the change in radius be dr, like the differential, dr, dt, because I'm changing the radius over time. The change in surface area we could say is dA dt, or the change in area over time. And then the change in volume over time would be dV dt. And so one thing you'll all notice is that the denominator of all of these is dt. That's what we mean when we say that something is changing with respect to time, okay? So all of our derivatives now are going to be over dt whenever we talk about things changing over time. Okay, so let's apply this to a question. So, example 1a. If the balloon is being filled with air at a constant rate of 2 centimeters cubed per second, how fast is the radius changing when the radius equals 3 centimeters? So one of the things I like to do is to go ahead and draw a diagram. And so I'm going to go ahead and draw a sphere. And I just kind of put like a little belt around it so I know it's a 3D object. And I know that for this particular balloon, the radius at the time that I'm interested in is 3 centimeters. Now, if I'm looking at the balloon being filled with air, this information right here, they're telling me, is actually the change in volume over time. That the volume will increase by 2 centimeters cubed for every second that passes. Now let's see what this question is asking. This question is saying, how fast is the radius changing? So what they want to know is dr dt equals what? And so what we're going to do is we're going to go ahead and come up with a formula. This is a good chance to review some of your formulas from geometry about volume and surface area. Those are going to come in handy for this section. So since I'm looking at the volume of the balloon, I'm looking for the volume of the sphere, which is 4/3 pi r cubed. Now when we're talking about related rates, what we want to do is find the derivative, okay? So the derivative of v is going to be dv dt, because I'm changing it over time. Now the other side might look pretty complicated, but I want us to remember that we have that constant multiple rule, and that 4/3 pi is a constant. So I can say 4/3 pi times the derivative of r cubed, which is 3r squared dr dt. So it's kind of like we always have to do chain rule or implicit, that we have that dr dt at the end of our derivative. Okay, once we've got our formula, and it's really important we double check our work right here, once we've got our formula, then we can plug in all the numbers we have. So I know the volume is increasing by 2 centimeters cubed per second, so that's my dV dt. The 4/3 pi is going to stay. 3 times the radius is 3 squared. And then I don't know my dr dt, but I want to find it. So let's clean this up a little bit, see what we can reduce and cancel. I notice that this 3 and that 3 can cancel. And so I really have 2 equals, let's see, 4 times 9 is 36 pi dr dt. And so dr dt is going to equal 2 over 36 pi, or we could say 1 over 18 pi. And the units for this are going to be centimeters per second. Now what this means is this, kind of like when we were talking about differentials, it's really important that we are able to understand what the numbers mean. So in this case, when the volume goes up by 2 centimeters cubed per second, the radius will go up by 1 over 18 pi centimeters per second. Okay, so that's what it means in terms of our answer. Okay, let's try a variation on this problem. So 1b says, how fast is the surface area of the balloon changing when r equals 3 centimeters? So we have the same information, but now we want to find out about the surface area. So I'm going to go ahead, instead of writing a volume formula, I'm going to write that the surface area of a sphere is 4 pi r squared. And so just like I did with the volume, I took the derivative. I'm going to want to take the derivative of the surface area. So the derivative of the surface area as it changes over time equals, now just like last time, this 4 pi is a constant, so I can keep that out front. And then the derivative of r squared is 2r, don't forget the dr dt. Okay, let's see what numbers we can plug in now. I want to find dsa dt. So I have my 4, my pi, 2 times the radius is 3, times I can use my dr dt from the previous part, 1 over 18 pi. Okay. Let's see what we have when we clean this up a little bit. We will get that the derivative of the surface area over time equals, let's see, 4 times 2 is 8, times 3 is 24. So I have 24 pi over the 18 pi that was there. The pi's are going to reduce. I'm going to get the change in surface area over time equals 24 over 18, or we could reduce that to be 4 over 3 centimeters squared because it's area per second. Okay, now let's make sure we know what this means. That when the volume increases by 2 centimeters cubed per second, then the radius increases by 1 over 18 pi centimeters per second, and the surface area increases by 4/3 centimeters squared per second. Okay, so a lot of information here, but it's very similar to differentials that when one thing changes, it's going to change something else. Okay, let's take a look at a question. So my question to you is this. If the volume is changing at a constant rate, are the radius and surface area also changing at a constant rate? And so to answer this question, let's take a look at example 2a and 2b, which are going to be super similar to 1a and 1b, except we're looking at a different moment in time. Okay, so for example 2a, if the balloon is being filled with a constant rate of 2 centimeters cubed per second, how fast is the radius changing when the radius equals 6 centimeters? So because I did this before, I'm going to write down the formula, 4/3 pi r cubed. I'm going to remember that 4/3 is a constant, so when I take this derivative, dv dt, I have 4/3 pi times 3r squared times, don't forget, dr dt. And I'm going to fill it in with my new numbers. So dv dt, this is still 2. I have 4/3 pi 3 times 6 squared times what I want to find, dr dt. Okay, what goes away here? This 3 and that 3 go away. And so I end up with 2 equals 4 times 6 times 6, which gives me 144 pi dr dt. And when I isolate my dr dt, I get 2 over 144 pi, or I get 1 over 72 pi centimeters per second. Now last time when I said what happens at 3 centimeters, we got 1 over 18 pi, and that's different. So what this is saying is at 6 centimeters, so when the balloon is bigger, the radius gets bigger at a smaller rate. So this radius is still increasing, but at a smaller rate. Now let's see if that's true for 2b. So how fast is the surface area of the balloon changing when the radius is 6 seconds? So I'm going to go ahead and copy my derivative equation from above, and we had 4 pi times 2r dr dt, and I'm going to fill in my different numbers. So 4 pi, 2 times 6, times, this time I need to put 1 over 72 pi. And when I simplify this, I'm going to get 2/3 centimeters squared per second. Okay, so what this tells me is that things are still changing. The radius is changing, the surface area is changing, but at different moments in time, they're changing differently. And so we're going to stop video 1 right here, come back for video 2.